Today I will cover linked lists in Python, which are similar to lists but store data differently. An element in a linked list is called a node. A node contains two properties: data, which stores any value you wish, and pointer, which points to the next node. So for example, node 1 points to node 2, which contains its own values and a pointer to node 3. The first node in a linked list is called the head, and the last node is called the tail. This here is an example of a singly linked list, because each node is only connected to another node via one pointer. Here is an example of a doubly linked list. It's called doubly linked because each node has both a previous pointer that points to the previous node and a next pointer which points to the next node. The final category of linked lists is circular linked. In this case, here is a doubly circular linked list. This is because the previous pointer of the head node points all the way to the trail node, and the next pointer of the trail node points all the way to the head node. This makes the list circular because if you continually call next, you will recursively loop through the list again and again as there's no stop point. However, in this video, we will simple singly linked lists. Let's look at a quick animation of how we delete and insert nodes before we start coding. Let's say we wanted to delete node 2. The first thing we do is update node 1's pointer to point to node 3. Then we can disconnect node 2 from node 3 and delete node 2. Now the deletion process is complete. Let's try insertion now. Say we want to insert a node between nodes 1 and 2. First, we connect the new node to node 2. Then we can disconnect the first node from node 2 and attach it to the new node. Let's get coding in Python. To start off, we'll make a node class. This class has two properties: data, which we will pass in upon creating the node, and next, which will default to none. Now that we have the node class, we can create a linked list. Here I've started off by creating 4 separate nodes, each of them having their own data value. Now we can connect the nodes together. Here I've set node 1's pointer to node 2, the second node's pointer to node 3, and the third node's pointer to node 4. Notice how I don't have a pointer for node 4 because node 4 doesn't have a next node. Now we can create the traverse method, which will iterate through the list and print each node. Here we'll pass in the parameter head and set the current node equal to this. Remember that head is the first node in the list. Now we can loop for while this current node exists, and we can print the current node's data. After we print the data, we can update the current node to be the next node. Now if we run this method, you can see that the first node prints, and then the second node prints, and the third node, and finally the last node. Now let's create a deletion method. We'll start by passing in the head, which is the first node in the list, and we'll also pass in the node that we wish to delete. We'll start off by setting the current node equal to the head. Now let's look at the special edge case of if we're deleting the head. First, we'll check if the head is equal to the node that we're deleting. If this is true, we'll set new head to the second node in the list. We'll delete the head node, and then we'll return the new head. It's important that we return the new head because to call other methods on the linked list, we typically need to have the head node. If we're not trying to delete the head, then we can iterate until we find the node that we wish to delete. To do this, we can check if the current node's pointer is equal to the node that we want to delete. If at any point during this loop, we find that the current node's pointer is equal to none, that means the node doesn't exist in the list and we can just return. Now the current node should be one left to the node that we want to delete. So we can set the deleted node equal to our next node. And we can set the pointer of our current node to the node after the deleted node. This way that all the nodes are still connected despite the one node getting deleted. Now we can finally delete the last node and we can return the head of the list. Now let's test our new function. So here, if I try to delete node 2, the second node is deleted. Now we can try the edge case of deleting the head node. And as you can see, the head is deleted and a new head is given. We can also try deleting a node that doesn't exist. So here I try it and there's no nodes deleted and there's also no errors thrown. Now we can create the insertion method. So we'll pass in the head, the new node we wish to insert, and the position. So once again, we'll look at the edge case first of if we're inserting it as a head. So if the position equals 0, then we'll set the pointer of the node we're inserting to the current head. And then we'll return our node that we're inserting as the head. Now we can carry on with the normal insertion case. So for this, we're going to loop until our current node is one left of the insertion spot. And for this, we're going to repeat position minus 1 times in order to achieve this. And at any point during the loop, if the next node is equal to none, we're going to break. This way, if we're inserting at a position that is greater than the size of the list, it will simply append the node that we wish to insert at the end of our linked list rather than giving an error. Now we can finally perform our insertion. So what we're going to do is we're going to set the pointer of the new node to the node after our current node. Then we can set our current node's pointer to our new node. And then finally we can return head. Now we can try our new insertion method. So here I'm inserting a node at position 0, which should be the head of the list. And as you can see, it's updated to be the head of the list. If we want to put it in the first position, which is the second node, we can do so by changing the position to 1. Let's try changing the position to something that is outside of the range of the linked list. Let's say 8. And as you can see, the inserted node is now added at the end of the list. Now let's compare the use cases and pros and cons for when to use list versus linked lists. To do this, I'm going to show you a graphic that represents memory allocation. As you can see here, a light green represents the memory allocated for a list, and the dark green represents the items in this list. Blue represents the memory that is already allocated to other needs, and yellow represents memory allocated to the linked list. The first point of comparison is deletion and insertion speed. So in this list, let's say we want to delete item 5. Then we would have to rearrange items 6 through 10 to fill in. However, in a linked list, if we want to delete node number 3, all we would have to do is update node 2's pointer to point to node number 4. In this way, it is much faster to insert or delete items in a linked list because you only have to change adjacent nodes, whereas in a list, you may have to update all the items. Additionally, it's more expensive for normal lists to resize. For example, if you look at this here, if you want to expand this list more than 12 items, you would have to reallocate this memory somewhere else and then fill in. However, in a linked list, if you want to add a new node, you could simply add it wherever there is free space. However, linked lists take up more memory. For example, this node here has to both store the data of the node and the pointer to the next node, whereas an item in a list only has to store the data for the item and not a pointer. Additionally, lists have better indexing. For example, in a linked list, I would first have to access items 1, 2, and 3 to then get to item 4. However, in a list, I could just directly access item 4. Finally, both linked lists and lists are iterable, but lists are slightly faster because their items are memory adjacent. Here is a table that illustrates these comparisons.